Thank you everyone for joining the meeting today and make time for this presentation. Today I'll be talking about the intact and the damage survivability of offshore floating moored oscillating water column device. This presentation was a part of my PhD back in the AMC and with my supervision team, as you see in the screen. And this presentation was meant to be presented in one of the international conferences in San Francisco back in 2017, but unfortunately I couldn't make it on time due to the flight delay. So I think it's a good time to present it today. I will start with the background about the oscillating water column. For who doesn't know about the oscillating water column, it's one of the simplest device to extract the wave energy. In terms of principle, it's just a chamber in the water, and as the wave propagates to the forward wall, the water level moves ups and downs, pushing and sucking the air through a unidirectional turbine. And of course, it can convert this mechanical energy into electricity. The motivation and the challenge in the oscillating water column device is most of the devices being deployed on the onshore and as a part of the pre-quarters or as a standalone device. And the problem with this onshore device is that you're not actually extracting more energy because the energy gets lost in the friction with the seabed, and some of the energy get lost in the wave breaking as the shallowing effect as the wave propagates to the shoreline. The next step is to move the device a bit more forward into the ocean, which is the nearshore device, which is shown in the second photo. The water depth normally between 10 and 15 meters. And the device is a concrete structure, sits on the seabed. But again, you're not extracting more energy as the offshore devices that's deployed in the deep water, where the energy is waves are more energetic. However, as we move from the onshore to the offshore, we increase the energy that we can extract, but at the same time, we increase the risk of losing the device in the harsh environment and the associated cost with the device to keep it floating in this environment. How we can make the device is a cost-effective mean to extract energy. We have two options. The first one is to optimize the device profile, which means we can extract more energy. The other thing is to optimize the structure design. We can do this by identifying and estimating the energy losses, and this can be done through an energy balance that I have done in my PhD as well. Understanding how the incoming energy is being converted into reflected energy transmitted and the energy losses within the device itself. And you can identify the areas where the energy gets lost and start working in these areas to refine the design and improve the performance. To optimize the structure design, we need to understand and predict the extreme loads and understand the device behavior in the waves. If you have any questions, just feel free to stop me. Don't have to wait at the end. And this is actually what I'll be talking today about, is predicting the extreme waves, predicting the extreme loads on the device. And the mooring system for the wave energy converters is not just to provide station keeping of the device and prevent any collision between the device and any surrounding structure. Mainly if you're talking about an array of the wave energy converters that actually very close to each other, and you want to make sure that there is no collision happening between these devices. But it also can be a part of the power take-off system. This may not be the case for the oscillating water column. As you can see, it's just a device in the water, and we tend to keep it as stationary as much as we can, especially in the heave motion, and rely on the movement of the water inside the device. But for other devices, just as a floating buoy that actually relies on the amplitude of motion of the device in the heave, and the mooring system is a part of the power takeoff that transfer this motion into the mechanism to extract energy, which is in the seabed, on the seabed. The mooring system for the wave energy converters has been estimated to be a huge amount of the capital cost, between 10 to 30%. Which is a huge amount that need to be visited to understand more the loads and try not to be very conservative in the design and accordingly reduce the cost. Here I'm just going to explain a few cases that actually happened in the past where the mooring line failure happened in the wave energy converters. One of them was back in 2004 in Denmark. This is one of the overtopping device. It's not an oscillating water column, but it's still a wave energy converter. And a failure happened in one of the mooring lines. The second one was in Australia back in 2010 in Sydney. And this belonged to Oscillating, which is one of the companies in Australia that was working in the wave energy converters. And this was an array of 8 oscillating water columns. The cost of this device was about 5 million. And mooring line failure happened in a few mooring lines, and the device ended up hitting a big water and sank. The main issue here is that most of the design for the floating moored wave energy converters relies on the existing codes, which is mainly developed for offshore structures. And using these codes and these safety factors, which are high safety factors because you're talking about losing the device and losing the people life on board, which is not the case. Most of the wave energy converters actually operates and manage unless you do maintenance or repair. Using these codes could be a very conservative and accordingly increase the cost of the mooring system in the wave energy converters. And the reason that we not actually intend to use the same factor of safety or the same design codes, because there are some main differences between the wave energy and the offshore structures. This includes the water depth. The floating moored wave energy converters will be deployed maximum at 150 meter depth. The initial frequency of the device is different from the offshore structures. The structure and the mass and the scale of the structure, again, is different. And the motion amplitude is different. For the offshore structures, you actually design the mooring system for the station keeping of the structure. But again, as I said before, for some of the wave energy converters, you tend to use the mooring system as a part of the power takeoff and try to magnify or increase the amplitude of the device to extract more energy. In most cases for other devices, you design the device to actually be around the resonance, so you can actually increase the amplitude and extract more energy. The mooring footprint is different, and the number of mooring lines that you need to use for the wave energy converters is again different from the offshore structures. So the objective of this presentation or this part of the research is that the DNV was actually using multiple limped states, including the ultimate and the accidental limped states. The accidental limped state is exactly the same as the ultimate, except that you disconnect one of the mooring lines and make sure the other mooring lines can actually take the rest of the loads. In that case, when you disconnect the mooring lines from the beginning of the analysis, you're not considering any transient effects that may occur when the failure happens as the device moves or interacts with the waves. So in this research, I was actually interested in using CFD and using experiments to understand the device behavior in the waves and predict the loads and see if the transient effect is really important to be considered or not. Here I'll be talking about the experiments and the CFD simulations. The experiment was done in the Australian Maritime College in Tasmania, in the towing tank, which is 100 meter length, 3.5 meter wide, and the water depth was 1.5. The model scale was 1 to 50, which converts into 75 meter water depth. There are a few wave props to measure the instant wave, and another wave prop G3 to measure the phase wave in front of the device, and some wave props to measure the reflection and transmitted waves. On the other side, for the CFD, the wave tank was a 3D model. the length was 12 wavelength, and I have done a study on how many wavelengths do we need to consider to generate the waves and not to have a lot of reflection from the end, and ended up having 2 wavelengths assigned for wave damping at the end, at the outlet, and the model was placed at 5 wavelength. The model was actually on the CFD using RANS, which is the range average Navier-Stokes equations. The turbulence model was K omega. Talking about the experiment setup, so the model was just a simple rectangular box. And as you can see in the top, there was an opening, which is an orifice with different diameters to represent the power takeoff or the damping induced by the turbine in reality. And this, during this experiment, because we're looking more in extreme condition, this orifice was closed to represent the extreme condition. At the survival condition, you don't need to extract energy, shut down the device. That's why we closed the orifice. And there are 4 mooring lines, 1 at each leg, and connected to the mooring pace. As you can see, each mooring line is connected to a load cell to measure the tension in the mooring lines. And there's a spring. The spring was chosen based on the prototype stiffness of the mooring lines and scaled down. And it goes through a pulley system and then goes to the side of the tank with the turnbuckle to adjust the pre-tension required and make sure that all the tensions in the mooring lines are equal. And this blue thing here, this is the electromagnet that is connected to one of the mooring lines to the forward starboard line to enable to disconnect these mooring lines to represent a failure in the mooring system. And these passive markers were tracked using 8 cameras to track the motion of the device. In the safety, the numerical wave tank with a 3D model, as I mentioned, and there's a refinement around the free surface to make sure we capture the wave profile. And the resolution of the free surface was as recommended by the ITTC, which in line with the mesh study that I have done, which is almost between 80 to 100 cells per wavelength and 20 to 25 cells per wave height. And this model was done using star CCM and using the overset mesh to allow the device to move. And I will explain the overset mesh very quickly here. So this is called the background mesh, which is a stationary mesh. And around the model, there is a small mesh refinement, which is called the overset mesh. And there's an overlap mesh. The overset mesh can move inside the overlap and make sure that the model actually does not move far apart outside the overlap, otherwise the solution will not converge. And basically the overlap transfer the information in terms of pressure and velocities between the overset mesh and the background mesh. And there are 4 mooring lines as well, 1 to each leg. And to enable disconnecting the mooring lines at a predefined time, I did try a macro that can run star CCM and disconnect one or more mooring lines during the simulations at a predefined time in this macro. Right, so before I go to the results, does anyone have any questions? No?
Yes, Ahmed.
Yes, please.
How is the actual configuration at sea or offshore exactly the same as that? Are the lines significantly tensioned to hold the buoy, at a predetermined height? I wasn't sure whether it was just mooring to say, stay around here, as opposed to specifically tensioning it to the seabed.
Actually, the reason to choose this kind of mooring, which is that kind of tension leg mooring system, is the water depth in the towing tank. and to simplify the model and make sure that we got a good results from the experiment to validate the safety. But talking about the reality, the tension in the mooring line has a slightly impact on the device performance. That's why I found in my research. And again, for this kind of device, which is oscillating water column, you don't need the device to move quite a lot. Otherwise, if it moves with the waves, the relative motion between the device and the water inside the chamber will actually impact the performance. So you're actually looking at the relative motion. So if you keep the device stationary and just relying on the water height inside the chamber, this would give more energy. But for other devices, you actually need the device to move. So a tension leg may not be the best choice for this. If that answers your question.
No, thank you very much. That was sort of what I was concerned about, in that I could also imagine that if you had a tension leg and you had some big waves, that you might actually get shock induced into the tension leg if the structure wasn't deep enough to maintain that tension at all times, no matter what the profile of the wave was. So yeah, I guess I've always seen mooring lines previously on offshore structures that are quite loose and have a constant, you know, a catenna to them. And when I saw this, I said, this is different than what I expected.
Yeah, actually, if the mooring, if the tension is not, if you don't have enough pre-tension, definitely you can get slack at some times, and you have this snatch load happening on the next cycle. Yeah, which I'm getting here in case of the failure as well, as you can see in the results I was just about to explain. And in this last figure at the bottom, you can see the mooring line goes slack and all of the sudden goes in tension. And you have this nonlinear effect because actually the model starts panging.
Yeah, can I just pick up on the fact that you're modeling vertical tension legs as opposed to anything with at any angle? Is that well, even if it was in tension at some angle or had some slack in it in catenary, what is done out there in practice? Does they tend to spread or try to keep it to the same plan profile for the foundation as effectively the floating element?
As far as I'm aware, with the oscillating water column, the devices that's being deployed as a prototype was of a catenary shape.
So there was some form of greater spread of the base than your experiment.
Yeah.
Yeah. Thanks.
Just one point before we move on. My experience in offshore structures more generally generally indicates that you have about 8 mooring lines used for a structure as against the 4 that you have done for this exercise. And if you had more mooring lines, that gives you less effect coming onto the floating the platform when one fails. So did you consider other mooring arrangements, such as having 8 mooring lines rather than just the 4?
Yeah, I did. Actually, I was about to discuss this in this presentation as well. I did consider 2 different configurations. One is 4 and one was 8. So we're having some mooring system redundancy in the system in case of one mooring line fail. Okay, I think Rob is not there.
No, I just unmuted, sorry.
Okay.
Just muted.
Yeah, so I'll just keep going, and if you have any questions, please just let me know. So the wave height we tested in this was 200 mil in model scale, which is about 10 meters in full scale. And in this top figure, we actually looking at 3 different results. The first one, the experiment results, when we initially disconnect the mooring lines before we run the experiments. So it's initially disconnected, doesn't have any transient effects, which is this line there at the bottom. The second one is the experiment when we disconnect the mooring line at a certain time, and the mooring line goes from some value suddenly to 0, and similar with the experiment and the CFD. And the port line, which is the forward line, this is the results when you disconnect the mooring line initially, it doesn't have any transient effect. And this is when you disconnect the mooring line at this instant, you have this transient effect. I will talk more about the transient effects. And when we did observe it, if it happens immediately at the instant of the failure or in the following cycle, depends when we actually disconnect it. And some of the mooring lines, especially the aft port line, which is in the diagonal of the disconnected mooring line, actually goes slack. And on the following wave, start taking more loads and have this nonlinear effect and go slack again, and so on. Some of the experiments. So I'll just play the video again so you can see the instant of disconnecting the mooring line. And this is just in the underwater. And this is the safety. You cannot see the agreement in this visualization, but there's some values that we can check the agreement. Is I'm still connected? It just says that my internet connection is not good enough. I'm still connected, or can you hear me?
Yes, we can still hear you and see you, so everything's all right.
Yeah, thanks. So talking about the transient effect, I did have 2 classification or 2 categories, category A and B. Category A, when we notice the transient effect, not at the instant of the failure, we notice it on the following cycle. And this normally happens when you disconnect the mooring line after the peak value of the tension. If you disconnect the mooring line or the failure happens at the peak or before it, then you actually suddenly notice the transient effect immediately at the instant of the failure. And to look at the importance of the transient effects, and we did actually disconnect the mooring lines at 10 different instances, including some experiments and CFD in terms just to compare the results. And the rest was done using the CFD. Of course, it's in the CFD, it's much easier to predefine the time, and it's more handy than the experiment once it's validated, of course. And here we're just looking at the 4 lines arrangements. We have 1 mooring line at each leg, and disconnecting the forward starboard line and looking more at the port line tension. And you can see the transient effect is about 19% when you compare this to the tension in the mooring line if you disconnect it without any transient effect. And this is all category B, which means that instant 2 and 3, or 3 and 4, which is this 2, which is just before the peak tension, gives you the maximum transient impact. And looking at 7 and 8 and 9 and 10, this is the comparison between the CFD and the experiments.
Sorry, what's category A and B?
Category A and B is A when you disconnect the mooring line after the peak. So you're actually not observing any transient effect suddenly. You just observe it in the following cycle. If I go back to the slide, this is category A. When you disconnect the mooring line or just after the peak, and this one just before the peak.
Yeah, sorry, I missed the labeling.
No, that's all right. I'll just put it here again. So the maximum transient effect was observed when we actually disconnect the mooring lines before the peak value. And looking at 8 mooring line arrangements with some mooring line redundancy, if we disconnect one of the mooring lines, now we have 2 mooring lines, two at each leg. If we disconnected one of them in the forward starboard side again, and looking at the tension in the port side, we found that the transient effect significantly dropped from almost 19 to about 11%. But on the other side, and the mooring line, which is left on the starboard side, actually the transient effect was 22%. To put this side by side, we have 2 different arrangements. One is 4 and one is 8. With the 4 mooring lines, we're losing 100% in case of a failure. And with the 8 mooring lines, we're using 50% of the mooring system at this leg. And looking at the results, the black scale is for the 100% loss and the red is for 50%. And disconnecting the mooring line 100% on the full mooring line arrangement results in a transient effect in the starboard side, in the port side, and disconnecting one of these 2 mooring lines result in a sudden increase in the mooring lines in the remaining line in the starboard side, and the mooring line in the port side increases as well, but not as much as when you lose 100%. Looking at the ratios, we have 1.5 times the intact tension when we lose 50%, and the transit effect was 23% in the remaining mooring line. And for the 100% loss, we increased the tension by 1.8 times the intact with 19% transit effect. In total, the tension increased with the transit effect to 1.85 times the intact for the 8 mooring lines and about 2.14, which means that with 8 mooring lines, we definitely have more redundancy and we have less likely to have any progressive failure because in this 100%, we actually increase the tension by almost 2 times the intact tension. So it depends on how much factor of safety we have in designing these mooring lines. We may over exceed this factor of safety and start having progressive failure in the remaining mooring lines. So just to summary up, it's always the mooring lines in the forwards experience the most of the tension for this kind of arrangement. And without any transient effect, we notice that it's 1.8 times the intact for the 4 lines arrangement and 1.5 times the intact tension for the 8 mooring lines arrangement. And the transient effect may be observed immediately at the failure instant or sometimes following the cycle, depends on when you disconnect the mooring lines. And there's about 90% transit effect or mooring line overshoot at the 4 lines arrangement and 23 in case of 8 mooring line arrangement, which is 50% of the mooring system. And this tells us that the mooring line redundancy to reduce the possibility of having any progressive mooring line failure. Of course, this research was done with only 1 wave height, which is a regular wave height. And you cannot actually have a generic conclusion based on this. And that's why I have done another research to include these factors to highlight the importance of using different irregular sea states in the survivability, including intact and damaged mooring systems, and the applicability of using only single regular wave to represent the regular sea states, because it's more easy to actually run regular waves even in the CFD. The irregular waves in CFD is very computationally expensive, and no one actually interested in doing this kind of simulations. And also to discuss how it's important to consider the instantaneous position of the mooring system, because it's not always the maximum wave height that gives the maximum tension. It depends on how the wave trains actually before this maximum wave height that may position the model in a state that when it's hit by small waves can generate more, can actually observe more tension.